So today I'm going to go over Fourier Fourier series. Yeah, probably everything is about Fourier series. So before I go to the real thing, let's do some review on complex number and the periodic thing. A lot of things, because you are going to need that in your Fourier series. So first thing is the representation of complex number. There are two representations. A plus j, b, and j is the imagined part. I guess all of you should know this. And the other thing is the polar representation. It's like r times e to the power of j theta. So let's visualize what is going on here. So if this is the plane, and this is not x and y, this is actually the real axis and the imaginary axis. And one complex number should be one location inside this plane. And if we use the coordinate to represent that, we're going to use the first form. So the length here should be a, and the height here should be b. So the representation of this dot is the first representation. And we can also use the polar form, which we measure the distance from the origin. This distance is r, and this angle is theta. So actually the theta does not have any limitations. It's like it can be negative or it can exceed 2 pi. So we can see this part, this is theta. We can also see, well, it go around and comes back here. This is also theta. This one is more than 2 pi. So usually we need to convert back and forth to between these two representations. So a plus b is equal to, well, the length. You know how to compute the length, r here, and theta here should be 1j here. Sorry, the theta. This is a little bit tricky because you have to decide the sign of theta based on which quadrant it locates. Like here, theta is positive, but here, theta is something negative, or something exceed pi. Well, but usually we're not doing this kind of transformation. Usually we're doing the other way back. It's like, but this is straightforward. You don't need to decide anything. So just use cosine and sine. This might not be on cheat sheet. But till now, I think you already got the cheat sheet. You can check what's on it and what is not on it. But I recommend that you remember this. This is pretty basic. So another thing is like the periodic property. Sine, cosine, we already know that. But another thing is the exponential function is also have a periodic property. So sine, cosine, we know that if you plus 2 pi k and 1k is integer, this one equals. And for exponential, it's like if we plus 2 pi here, it still equals. It's like we rotate theta to get this angle, and if we rotate another term, we still get this angle, or if we rotate backward, but till here, we still get this angle. So it's periodic. So Euler's equation, I guess we already discussed this before, and it's very useful because when we are doing Fourier series, when we see just the sine and cosine, usually it's easier that we change everything into exponentials and do the simplification. So let's try some examples. So what are the values of this? Well, try to simplify this. So first one, anyone want to have a try?
Is it cosine pi, which is 0 plus j cosine pi, which is -1, so negative j.
Cosine
Is it final answer is negative j?
pi. Cosine pi.
-1.
Yeah, cosine pi is -1.
And then okay, so the answer is -1.
Yeah, sine pi, and this one is 0. So the answer is -1. Actually, if you are a fan of Euler, this is a very famous equation, like e to the power of j pi equal to -1. Yeah. And second one, let's add something like k here. K is an integer, but still it does not change the thing. So who want to try this one?
So it's 1.
Can you show the step here? Like,
cosine 2k pi.
okay, cosine 2 k pi. There's actually one minus here. Yeah, negative 2 k pi.
Negative
Yeah, plus
j sine
plus
minus 2k pi.
minus 2 k pi. So what is this?
So cosine will be like positive and sine will be negative.
Cosine is negative beta. No, cosine beta, right?
Well, let's say k is integer. So what do you see here?
So you want us -1 plus 0 is 1.
It's -1, right?
Yeah.
So cosine minus 2k pi is 1.
So because this is 2 pi here, so it's sometimes 2 pi, and 2 pi is just turning around and returns here, right? Yeah, even though it's negative, you're turning it clockwise. Clockwise is negative. Even though it's negative, but because you are turning 2 pi, multiple times of 2 pi, so you always return to the original location. So, well, this is equal to 0. This is equal to cosine 0, right? Plus this is j sine 0. So this is 1. So if you visualize that, so because here the r equal to 1, so here we can use one vector, like the length is 1 here, and it turns multiple times and back to itself. So it's 0. So these are two ways you can find the answer. So the third one, I'm not so sure, but if I grade the exam, if you get this kind of answer, probably I'm going to give you a point, but I don't know if professors think this is simplified enough, because this can be simplified into sine or cosine. If you see a number like this. So I'm going to do that. The first one, let's keep it because it's pretty simple. The second one, I think 503 is sort of big number in amplitude. So I try to see if it is another number in another period. So I use J 3.5 pi minus 2 pi. So because it's periodic, it does not change the number. So this one become negative 3 pi. So this one become j to the power of e to the power of j pi over 3 plus e to the power of minus j pi over 3. So in the Euler's formula, you see something very similar here. So we try to fit into this formula. So because there is 1 over 2 here, so we put over 2 here and put the 2 outside. And inside this parenthesis, it become a cosine. And this part is the theta, so pi over 3. And cosine pi over 3 is 0.5, and this one is 1. Question?
Why did you get the negative 2 pi?
Which is negative 2 pi? This one?
I can't see anything.
Oh, sorry. Like this negative 2 pi?
Yeah.
Because it's periodic by 2 pi.
And so how come you only subtracted that from the second root number? Not the first one? Like you only subtracted it from
Yeah, because I want to make this one somewhat similar to this one. Can see that?
Okay.
I want to make 5 over 3 somewhat similar to 1 over 3. Yeah, because I can get 1 pi over 3 and 1 negative pi over 3, so that fits the formula in Euler's formula.
And so you could just subtract any of them by 2 pi.
Yeah, any times of 2 pi. Yeah. So because we say they are periodic, so we want to know what are the period, or most of the time we want to know the inverse of the period, that is the frequency. So actually there are two kinds of frequency. One is the real frequency we can measure like in hertz, and the other is angular frequency. In this course, mostly we are talking about angular frequency. The most of the time you will see something pi, or when it's represented in omega, that's angular frequency. So how to decide the angular frequency of some component? It's like if you see sine sometimes of t, this is angular frequency, and in exponential you see j something t, and this is angular frequency. And then we come to fundamental frequency. So because most of the time we don't have just the one component, we have multiple components. So we want to know the fundamental frequency of the system based on the frequency of each component. So the way to decide this is to find the GCD of all of them, the greatest common divisor. And one thing to remember is like the fundamental frequency is always smaller or equal to any of the frequencies. It's like it cannot get larger, because sometimes some problems ask about the fundamental period. It's always larger than all the periods. So that's another problem, but usually we just care about the frequency. So this is the relationship of angular frequency and the period. So one example is like, what is the fundamental frequency of this system, or this signal, I should say. Yeah, it's 5 or 4. So actually we can tell like from these numbers, and let's try to do that step by step. So we take the frequency of each element, and the first frequency is pi over 2. And this one, even though it's in the summation, but we can see each one in the summation is actually one part of the signal. So we take out this part. So it's minus k pi over 4 when k equal to 1 to infinity. And for this one, it is 3 pi over 4. So we take the GCD of all these possibilities, and the GCD is pi over 4. So that's the fundamental frequency. Yes. So then we can come to the Fourier transformation, but before I discuss problems about Fourier series, I want to motivate you guys talk about what actually Fourier series does. Yeah, it's like, well, there are actually 4 kinds of Fourier transformation in general. So there are, here in the task we are going to see Fourier series, and after that in the book we are going to come with Fourier transformation. And actually this can be continuous time Fourier series, continuous time Fourier transformation, and there are discrete time Fourier series and discrete time Fourier transformation. So I'm going to call the whole thing Fourier transformation in general, to see how why we need all this messy thing. So I want to say Fourier transformation is one kind of machine that you give time domain signal as input, and the output will be an frequency domain signal. That means the output will be nothing about the time. It's about, everything is about frequency. So, well, you see, it is transformation of the signal. Actually, what we are going to use that is the transformation of a problem. It's like before we have a problem in time domain, and it's a little bit hard to solve. So we want to transform this problem into frequency domain and try to find a solution inside the domain and transform the result back to time domain. And the exact usage is like, in time domain, the output of an LTI system is the convolution of the impulse response and the input signal. So because convolution is something hard to compute, so we want to transform this problem into frequency domain. It's like, in frequency domain, convolution become product. So I want to put mathematically in this way, yt is time domain output. It is the convolution of the input and the impulse response. And I can compute that by first compute by Fourier transformation, what is the frequency domain signal? Is this and this, and find the product of them, and do the inverse Fourier transformation to find the final result. So if you still think that is a little bit abstract, I don't know if anyone have played this game before. I want to use this as a parable, like discuss why we need Fourier series. It's like in this game there are actually 2 worlds. One is the real world, and the other is called Nether. It's like another world. Like, so they have some relationships. So like this is the real world, and this is Nether. And you can open up a portal like here, and by the portal you can go into the Nether, and you can still open up the portal in Nether and go back to the real world. So there are some relationships, like taking one step in Nether is like taking 8 steps in the real world. It's like if you want to march to one destination, and you can actually from the real world open up a portal, go to Nether, and like maybe this distance is 1 mile. And actually when you go back to the real world, you end up somewhere 8 miles away from the original portal. So this is something very similar to Fourier series or general Fourier transformation. So the real world is what we have is time domain, and the portal go to the nether. This nether world is frequency domain, and the portal goes to nether is the Fourier transformation, and the portal goes back to the real world is the inverse Fourier transformation. And here, this relatively longer distance is some more complex computation, is the convolution. And this relatively shorter distance is the product. So to get the result, so this is the input and this is the result output. So to get the result, you can either do the convolution, or you can, by Fourier transformation, go to the frequency domain, do the product, and go back to the time domain and get the same result. I wish this can help.
Is there ever a time when you can't do the Fourier transform, so you have to do the convolution?
Yeah, some of the time, if the signal does not have some property you need for the Fourier transformation, like if it is not stable, you need to do other things like Laplace transformation. Yeah, but Laplace transformation is similar thing. It's like you go to another domain, solve a simpler problem, and go back to transform your result. Similar concept. So let's do some Fourier series problems. So first kind of problem is like there are only sines, cosine, and exponential. So these are the steps of you trying to solve this problem. It's like if you see one problem given like, well, this is the signal, do the Fourier series, and inside the signal you only see constant, sine, cosine, and exponential as its component. You can use this way. So first thing I recommend is change everything into exponential, including the constant, because you are going to see a zero inside the constants. And second thing is try to find the fundamental frequency. So if you try to find fundamental frequency, that is by because you see all the exponential has one frequency, you try to find the fundamental frequency of all these components. And then you can find the index and the coefficients based on the exponential expressions. So there might be a fifth step. If it is possible, transform back to sine and cosine. So let's do one example.
Could you go back real quick?
Yeah. So let's do this example. So first thing we want to do is transform everything into exponential. So we see this is a product of sine and cosine with different frequency. If you try to manipulate the sine and cosine, it's a little bit difficult. So, well, don't worry about that because we are in exponential, or we are going to be safe there. So we have 2j, which is sine e to the power of 2 pi t here. So it's j pi over 2, sorry, pi over 2 t. Because it's sine, so this is minus e to the power of minus j pi over 2 t times cosine here is 2, and here is e to the power of j pi over 4 t plus e to the power of minus j pi over 4 t. And we're going to find this one multiplied with this one. And can you see the cursor here? Not very easy. Okay, we're going to find like this one. Well, so this one multiplied with this one plus this one multiplied with this one. So everything you know mathematically, and we are going to have 4 terms. So this equal to, let's take this 2j and 2 outside. So here is 4j times. So here is e to the power of j pi 2t's. So this one plus this one, multiplied by this one is like e to the power of a times e to the power of b is actually e to the power of a plus b. So we can have this one plus this one. So you have j 2 pi over 2 plus pi over 4t. And we do the same thing for the rest. And let's do this one multiply this one multiplied by this one is e to the power of j pi over 2 minus pi over 4 t plus e to the power of j. This one is because this is minus, this is plus, so this should be minus e to the power of pi minus pi over 2 plus pi over 4 t minus e to the power of j minus pi over 2 minus pi over 4 t. And let's simplify it a little bit. It becomes 1 over 4j e to the power of j 3 pi over 4 t plus 1 over 4j e to the power of j pi over 4 t minus 1 over 4j e to the power of j minus 3 pi over 4 t minus 1 over 4j e to the power of j minus, oh sorry, this one should be pi over 2, yeah, minus, this is 3 over 4 pi t. So this question?
I think that isn't the third term supposed to be e to the j minus pi over 4?
Pi over, yeah, you're right. Thanks. 4. Yeah. So this part is its frequency. So we try to find the GCD of all of these frequencies, and obviously the GCD of 3 pi over 4 is plus or minus, and plus or minus pi over 4 is pi over 4. So next we are going to conclude the Fourier series coefficients. We need to take care of two things. One is index and the other is the value. So the index of the first one is this frequency is how many times of the fundamental frequency. So it's 3 pi over 4 over pi over 4 is 3 times. So the index here is 3. And the value of this coefficient is what's before this exponential. Is 1 over 4j, sorry, 1 over 4j. And the next thing, we can do the similar thing. So pi over 4 is 1 time of pi over 4, that is a1. And the value is what's before that is 1 over 4j. So question?
Oh, what did that say, A3?
Yeah, it's 3.
And that's representing the first e to the j 3 pi over 4 times t.
Yeah.
And there's alpha.
It's well, sometimes.
There's alpha negative 3 and alpha negative 4.
Yeah. So, well, you use alpha?
Yeah.
Yeah, well, I think, well, probably the same thing.
Yeah.
Yeah. So well, this is negative 1 equal to minus 1 over 4j, and negative 3 equal to 1 over, negative 1 over 4j. So, or other ai equal to 0.
How do you get 1?
Yeah, this 3 is you see the frequency here, right? The frequency of this component is 3 pi over 4. And we got the common frequency, the fundamental frequency of the signal is pi over 4. And how many times is this frequency to the fundamental frequency? 3. So that's A3. Yeah. So one thing you want to check out is there any partial index like A.5? So that's a sign that is showing the fundamental frequency is something wrong. And also, if you get the result is nothing but A2, A4, A8, well, it also shows maybe the fundamental frequency is wrong. Because actually you can divide everything by 2 and still get integers.
Why is that the
So
because you didn't pick the greatest common denominator?
yeah, you didn't get. If you use this, actually you are getting a too small fundamental frequency. Yeah, too small fundamental frequency. So next thing is the thing you mostly see in homework 4 is how to find Fourier series by its definition. So there are 2 directions. It's like the first thing tell you how to get the signal. What question?
Oh, so was that it for the last problem? Like we just find the A's and that's the end of the problem, or?
Yeah, that's the end of the problem. So series means you get a series of numbers in frequency domain, and that are A1, A2, A3, and that's all you want.
Okay. And something like this is what's going to be on the test, right? Like Fourier series.
Yes, yes.
Probably not.
Question?
So this is the final answer?
The final answer is A3 equal to A1 equal to, and at the end, all other A1 equal to 0.
Okay. And what were you saying with A2, A4, and A8?
That's this is something after the problem. I want to say like how to check if your answer is right. Yeah, if you say 8.5, that means your answer is not right. If you say A2, A4, A8, and nothing else, that means, well, actually you can divide all the index by 2, still get the integer. That means the fundamental frequency is too small. You actually need a larger fundamental frequency to get A1, A2, and A4.
So they should be non-divisible by values other than 1.
Yeah.
It can be alpha too. It's just that if all of them you divide by 2.
Oh, all of them?
Yes.
Okay.
Yeah, if all of them can divide by something and still get an integer, that means something is wrong. Yeah. Question? Oh, yeah. Okay. Then let's go to the definition. So you can see this is definition or not, but this is actually a pretty fundamental thing for Fourier series. First is like if you got all the A's, how do you get xt? Is like transform the series in frequency domain back to the time domain. It's something called synthesis. The second thing is like if I get ft, which is in time domain signal, how can I get the A's like before in the previous example? And A's are in frequency domain. So usually the second ones are more often than the first one, but the first one can still be there. By the way, this on the cheat sheet. Question?
So that bottom formula, that's the analysis formula or something?
That's analysis formula.
Is that what we just did in the last problem?
Hmm?
Is that what we did in the previous problem?
We did discrete time.
Yeah, that's what we did in the previous problem, but I didn't use this equation.
So we could have used that equation.
We could have used that equation, but in that way, you need to do the integrals.
Okay.
Integrals are fine. Well, yeah, if you always save using this, but probably it will make your solution longer. Yeah, and easy to get error. Whatever, I want to erase that. I don't know, it does not recognize the eraser. Okay, so the example, this is actually a homework problem. like so well, the first well, the problem give us a signal. It's a piecewise. We don't need to draw that, because as long as we know that it's piecewise, we are fine using the definition. And this problem often give us either fundamental period or fundamental frequency, because in the previous, sorry for this messy, because here we need period, and we need the frequency here, and we also need a period here. So we need both, but actually they are the same thing because we can calculate one by another. So let's do this problem. So first, because the frequency is given, so let's try to find the period. T equal to 2 pi over omega 0. That is 2 pi over pi is 2. And let's check this piecewise equation. So from 0 to 1 and 1 to 2, that means from 0 to 2 is just one period. So it describes everything inside one period. So we are safe to just apply the equation here. So the equation, let's copy that. AK equal to 1 over t, integral from 0 to t, f t, e to the power minus j omega 0 k t dt. So let's plug in what we already know. So t is 2, so this is 1 over 2 times, don't do this. Well, let me try to reopen it, make the eraser working. Okay, it's working now. It's also, this t is 2, so from 0 to 2, ft we'll take care of that later, and e to the power minus j, omega 0 is pi here, so it's pi kt dt. And then we want to divide this ft. Because we know it's piecewise, we break this integral into two parts. So the first part is from 0 to 1, and xt here equal to a number 1.5, so here is 1.5 e to the power of minus j pi kt dt, and plus 1 over 2 times, another piece is from 1 to 2, minus 1.5 is this value, e to the power minus j pi kt dt. So then if we solve these two integrals, we will get the final answer. Then let's try to solve that. Let's see if I have more space for that. Need this. So let's first copy what we had before. Is half 0 to 1, 1.5 e to the power minus j k pi t dt plus 1 to 2 minus 1.5 e to the power minus j k pi t dt, close So 1 over 2, as we know that the integral of e to at should be 1 over a e to at, right? So this one become 1.5. Let's take this out, and inside is minus j. K is always considered as a constant, so we'll take it here, k pi, and e to the power minus j k pi t. That it is from 0 to 1, and this is something similar. It's minus 1.5. E 1 over minus j k pi e to the power of minus j k pi t from 1 to 2. And then just try to solve this 1 over 2, and this 1.5 is something common, so we take it out. It's 1.5, and this 1 over minus jk pi is something common, take it out. 1 over minus jk pi, and inside here is e to the power of minus jk. First is t first is 1, so k pi times 1 minus this 0, so it's e to the power minus j k pi times 0. And here is minus, because here is minus sign here. Have e to the power of minus j k pi t is 2, and minus, because here is minus 1. So we have plus e to the power of minus j k pi times 1. Okay. And this part is 0. So e to the power of 0, this one is just a 1. This is something we have in the previous example. It's 2k pi, even though it's minus. So it's 2 pi something. So this one is also 1, right? We did it in the previous example. So, and this one are the same. So we can simplify it as 1.5 over 2. Let's write in a nicer way. Is 3 over 4 and minus j k pi. Yeah. This became 2 times e to the power of minus j k pi minus 2, and this 2 can be cancelled with that 4 outside, so this one becomes 2, cancel this 2's. So the only thing a little bit ugly left is e to the minus k pi. So let's try to view it a little bit. R is 1, so before rotation it is here, and the length is 1, and the rotation is the angle of rotation is minus k pi. So minus means clockwise, and pi is half of the circle. So if k equal to 1, that means it rotates here. If k equal to 2, that means it rotates back. That means if k is odd, then e to the minus j k pi is minus 1. If k is even, this one equal to 1. Can you get this part? So that means this one can be simplified to 3 over 2, 1 over minus j k pi equal to minus 1 minus 1 is minus 2 if odd, if k odd, and equal to 1 minus 1 is 0 if k even. And if we continue to simplify this part, minus 2 can be cancelled with that 2 and that minus. So this 2 disappear, this minus disappear, and just a 3 here. So this is the answer. Question?
Why is I see why the first one is 1, right? Why is the third term over there also 1? E to the negative jk pi 2.
This one? It's like when k is odd, that means it is rotated to rotated by 180 degree.
No, like above that. In the third line,
In the third line here,
I can't see where you're right.
you mean the second one?
Yeah, like that.
See your writing?
Yeah, we can see it. Like where you're right.
You're writing right now?
Let me try this. Are you mentioning this part?
Yeah, that part.
Because 2 pi means rotate the whole circle,
Right.
return to the original place.
So you're back to zero.
So it's like it is 1 rotate by whatever number of cycles back to 1, so it is still 1.
Right.
Question?
Can you explain the k is odd, e to the minus jk pi equals negative 1?
So it is something similar. So k, so this one r equal to 1. So before rotation, it is here, right? So when k is odd, that means, well, you see here is k pi, right? So it's sometimes of pi. So it's sometimes of half cycle. So if you have odd number of half cycle, you rotate to the back. If you have even number of half cycle, that means you have integer number of cycles. That means you rotate back to the original place.
So e to the negative j2 pi is
Equal to 1.
because minus 0.
Because because it's 0 plus whatever times 2 pi, and e to the power of 0 is 1, so they are the same because periodic. Yeah. Any question about this?
Can
Question?
you explain one more time why j 2 pi negative 2 pi is 0? E to j. So, like, yeah, whole idea.
Yeah, e to the negative j 2 pi, like this one.
Yeah.
I tried another color, like this one. So, I always say things in rotating things. Let's try another way, like expand that into sine and cosine. Okay, so we see the theta here is minus 2 pi. So this equal to cosine minus 2 pi plus j sine minus 2 pi. So cosine minus 2 pi is
So,
So cosine looks like this, right? So here you reach minus 2 pi. So this is 1 plus j sine minus 2 pi. Sine looks like yeah. And at minus 2 pi it is 0. So plus j times 0, that equal to 1. Does that make sense?
oh, okay. Alright.
Okay, still any question about this problem? Yeah. Okay. Then let's do let's do this example. This is about synthesis, like transform AKs to XT. So transform from frequency domain back to the time domain. So in this problem, usually we got omega 0 given or t given still. And what we are doing, we just want to use the equation here. We're going to use the equation here. So let's open up another one. I'm going to copy the first A here. So it's like, well, I forgot here. Well, I need to copy it here. Is 0 equal to 3? Well, let me just do it here, okay? It may be a little bit crowded. So, well, the equation we want to use is xt equal to k from minus infinity to infinity. That means every non-zero, ak times e to the power of j k omega 0 t. So that means we want to add these things. Let's plug each one by one. So the first is a0. So ak is 3. Here is a0 times e to the power of j. K here is 0. So 0. Omega t is 2 pi t. So again, this is a0. This 0 is the I here, index. And this 2 pi is the omega 0. And then plus next thing is 6j e to the power of j 2 pi times 1, 2 pi times minus 1, so minus t. And plus minus 6j, so minus 6j e to the power of excuse me, this should be 1, sorry. It's too messy here. So this is a1, so this index should be 1, and this is a minus 1, so the index here should be minus 1. J 2 pi times minus 1 t plus 3 times e to the power of j 2 pi, and index here is 4 t plus 3 e to the power of j, and is minus 2 pi t, 2 pi 4. Actually, I should put minus sign here. So this is 2 pi times minus 4t. Okay. So if you want to simplify this one, actually this can be simplified because you see some symmetric thing here, and it's hopefully we can use the Fourier's formula to simplify this into sine and cosines. So let's go to another board. So open another board, and this one equal to, simplify this a little bit, 3 plus 6j, and before here is e to the power of j 2 pi t minus e to the power of minus j 2 pi t, and plus 3 times e to the power of j 8 pi t plus e to the power of minus j 8 pi t. So we see one minus sign here, probably we can get one sine here, and we see a plus sign here, probably we can get one cosine here. So we try to use Euler's formula. So we put 2 down here, 2j down here because it's sine, and we have to make up another 2j here, and we put 2 here, make up another 2 here. Question?
Well, why isn't the 2 trying to equal to 1? Like what you did before?
No, because here is an t here. So before is like 2 pi k, right?
Yeah.
2 pi k is one integer, so it's either 2 pi, 4 pi, or 0 pi, or minus 2 pi. So everything is 2 pi times one integer. But here t is a real number, so you can count 05 times 2 pi, so that cannot be cancelled. Yeah. That one is discrete in frequency domain, but here is continuous in time domain. So question?
Where do you get the 6J from? Because I might have wrote it down wrong, but the way I wrote it, I got it to cancel out.
There is one minus on here.
Can you go back to the original page where you wrote down the expression?
So 6J here is minus 1 here. Minus 1 here. So this can you see the cursor?
Oh, no, it's just the dot of the J.
Yeah, here is 2 pi t. J 2 pi t here, and J 2 pi minus t here. So it does not cancel.
I got the dot on the J.
Yeah.
A dot on the J?
Yeah.
Oh, sorry. Yeah. Oh, yeah. Make sure you don't confuse yourself in the exam. Sorry to confuse you.
Where did you get the 3?
3?
First 3.
First 3. 3 is here. 3s are here.
Right, it's common factor.
It's not common because it's not automatically common because these are 3s from the given coefficients. These are the 3s. Can you see my cursor?
Yes.
Yeah, this 3 and this 3. So this 3 and this 3. And then I take the 3s out. Okay, then we can continue. Like this is 3 plus 2j becomes minus, so here is minus. Minus 6 times 2 is 12. And here is one sine, so sine 2 pi t. And plus 6, and here is one cosine, so cosine 8 pi t. Yeah, so this is a more concise result. So usually in this synthesize problems, well, it's better to transform everything back to sine, cosine if possible.
But on the exam, you don't have to.
I suggest you to. Yeah, it's like every problem. It's like you want to convert every sine, cosine into exponential, and then you get the result in exponential, and simplify it. Well, for your best, and then convert the result in exponential back to the result in sine and cosine. Yeah. I'm going to do that later. Yeah. So the problem can also be shown in this kind of form, like in C. You got this A case in figures like, well, this just mean A minus 2 equal to 3, A minus 1 equal to 3, A0 equal to 2, and A2 equal to 3. So you can read this figure as this coefficients. So everything else is the same. So any questions about this synthesis problem?
Do we need to drop the graph in the end?
Based on the problem, usually you do not need. Yeah, like xt, usually you don't need to draw xt. It's a little bit complicated. But ak, sometimes you might need to draw AK. And then let's go to something a little complex, the properties, and these are going to be on the cheat sheet. And if you check online, there is already a cheat sheet. If you have the book, it's on page 2.6, table 3.1, and all the whole chapter is about properties. So I will do 2 examples in homework, and if you have already read the homework solution draft, I'm sorry there are some error there. I have not changed that, but I'm going to explain here and going to update the solution later. Question?
Do you know like what time the new homework solutions are going to be up?
Well, it's like the draft is like these 2 parts are some errors here, and especially that even and real thing is wrong, but other things are not concise enough. Yeah, maybe I'm going to update the draft first because LaTeX takes a lot of time. Yeah, update the draft is easier, but I'm explaining it here. Question?
I just wanted to ask, like you posted like .mht files, whatever, into an Explorer. Is it possible to export them as PDF?
Well, the problem is if I export them as PDF, some equations are divided into 2 pages, so it becomes a little bit not readable.
Okay.
So that's why I try MHT. So are you using Mac? That's the problem. Well, I'm going to upload a PDF, but some of the equations are going to be divided into 2 parts. That's a little bit hard. Well, another way you can use SyncSci.
You could screenshot. I don't know how many slides there are. You could just screenshot the slides and throw them into a zip or.
Yeah. That's also a good idea. Yeah. Well, if before I can do that, you can use SyncSci because it's Windows. Yeah, virtual SyncSci. Yeah. Well, let's do this. These are 2 problems in the homework. First, this problem uses 2 properties. One is the time shift. You see t-1 and t+1, these are time shifts. And the other one is linearity because you have this plus sign here. If you don't have linearity, you cannot automatically add them up together. But here you have the linearity property, so you can do that. And it is not given specifically what AK the expression for AK, but we can just use AK in our result. So let's do this. Well, I think the first problem asked is what is the fundamental frequency of x2? Because we know that time shift does not change the frequency, so the frequency of this component is W1. Also, the frequency of the second is the same, it's still W1. And we want to find the GCD of W1 and W1, and of course it's still W1. So the fundamental of frequency W2 equal to W1. So we just use, I should say omega. Yeah. So we just use omega to represent the fundamental frequency. So let's do this. On the table, you have the time shift property. If you have this, if you have xt and you have its Fourier series to be AK, and then the Fourier series of xt minus t0 will become e to the power of minus j k omega, that is fundamental frequency t0. So this t0 is the shift times ak. So we can use that and plug in 1 and minus 1. t minus 1 have the Fourier series e to the power of minus j k omega. T0 here is minus 1, so here is plus times ak, and xt plus 1, the Fourier series of this is e to the power of minus j k omega, and t sorry here t0 is 1, here t0 is minus 1, so here is 1 and here is minus 1 times ak. And then by linearity we can add them up together, so xt minus 1 plus xt plus 1, and the Fourier series of this is these two add up together. So let's take ak outside, and inside is e to the power of minus jk omega plus e to the power of jk omega. And again we see this plus here, so by Euler's equation we can make this cosine. So let's put 1, 2 beneath it and another 2 here. So equal to 2 ak cosine, and omega is, I should say inside cosine is k omega. Or in this problem is k1 omega. Well, same thing, because every fundamental frequency is the same. Any question about this? Oh. You can check these properties on cheat sheet whenever you need them. Then the next example is still these are about properties. It's like which signals are real and which signals are even. So first thing we need to look is these are actually synthesis equations, right? So here is something we don't care about. This one is the fundamental frequency, but well, we don't care them too much, because what we need is just a case. We can decide if a signal is real or even just by a case. So a case are here, and the range of k is defined by the range of the summation. So by the property that is given in the table, if the signal is real, let me write it here. If xt real, then we have ak has some ak should behave something special, like ak. Oh, sorry, I write this absolutely. The easy way to check that is by checking the real and the imaginary part to see if it is conjugate. So ak should be conjugate. Ak should be conjugate to ak minus k. That means the real part of ak equal to the real part, real part of a minus k, and imaginary part of ak equal to the minus imaginary part of a minus k.
I thought it was a symmetry and not something even and odd. I thought it just like the graph and the real part had to be symmetric. I guess
It's like well, my solution was wrong. Yeah, so my solution draft on the blackboard was wrong, and sorry, I still didn't update that. So this is what is on the book. and on the book is section 3.5.6 or something like that. Well, you can, by the way, you can check that. 3. Conjugate 3.5.6 by conjugation and conjugate symmetry. So it's not direct symmetry, it's conjugate symmetry. That means the real part is even and the imaginary part is odd.
Okay.
Yeah. What?
Okay.
Question?
Because like in some of these examples, if you end up getting like the real or imaginary parts of the AK is just 0, what does that mean? Is that
Well, all 0 is both even and odd. All 0.
it would still apply to this?
Yeah.
Oh, it does. Okay.
All zeros, because here all zeros, you can see the real part of 0 is 0. So if AK is 0, A minus K is 0, so the real part equals. So it's even. And the imaginary part is all 0, so AK is 0 equal to minus, A minus K is also 0. So 0 equals minus 0, so it also holds. So all 0 will satisfy this condition. So sorry about the solution part. So let's check this condition for 3 of these signals. First one, it only have coefficients from A0 to A100. That means the domain itself is not symmetric, neither odd or even. So this one is not real, definitely. If we want to show that, you can say A1 equal to half and A minus 1 equal to 0, so it's not. It does not satisfy. So the second part, you can have like A minus K equal to cosine minus K pi, and you know cosine is symmetric, so is cosine K pi, and AK is just the cosine K pi, so they are the same. So so the real part is even, and the imaginary part, because the signal is pure real, because AK is pure real, you don't see any J here, you don't see any exponential here, so the imaginary part are all 0, and all 0 satisfy this all signal thing, so it should be real, so X2 real. And the third thing is A minus K equal to J sine minus K pi over 2 equal to minus J sine K pi over 2 equal to minus A K. And because this is pure imaginary, there's no real part of AK. So real part are all zeros, so this one is satisfied, and the imaginary part given by this one is satisfied. So so this X3 is also, thank you. It's also real. So is this clear? Question?
If you were to classify X1, would you say it's not real or would you say it's imaginary?
Classify X1.
X1?
Hey, then you give us conditions.
It's not real.
You say it's not real.
It's not real because imaginary means like it does not have a real part, and it is complex definitely, but I'm not sure is it imaginary or not. Pure imaginary. So the next question is asking, are these signals even? So but there is also a property 3.5.3, given that x minus t has a Fourier transformation, Fourier series minus ak, right? Am I right? Yeah. So that means let me see. Oh, yeah, that means if the signal is even, which is xt equal to minus x minus t, that will give us ak equal to, hold on, I'm not so sure about this again. SI 3.5. Oh, sorry. The minus sign should be here. That's what make it should be a minus k. So that means ak equal to a minus k. So that means if x is even, ak should also be even. The other way also works. If ak's are even, sk should be even. So that means if we check if ak's are symmetric, then sk should be symmetric. Even. So still this one, the range is not symmetric, so it cannot be even. The second is like, well, ak, well, here we have already got it. A minus k equal to ak, so it satisfies this part, so x2 should be even. And the third thing, we have a minus k equals minus ak, so it is odd instead of even, so x3 is not even. Question?
So if AK was odd and then X was also, oh wait,
Yeah.
okay. I was thinking if the frequency was odd and the AK was odd, then like Errata times the odd is even.
I didn't check that, but you can check it all. Like,
Instead of like remembering the formula, you can do it empirically. If you find if AK is odd or even, and then you look at the exponential, and then you can tell if that's odd or even, and then just use the properties of odds and even, odd and even.
yeah, sure. Yeah, you're right. But yeah, the usually is like well, just by looking at AKs. Yeah.
So how would you evaluate if the exponential was even or odd?
Well, divide that into sine, cosine, see, because sines are odd, then cosines are even. Yeah. Question?
So I'm a little confused about the definition of purely imaginary. Does that mean
that means if xt is pure imaginary, it's purely real. That you know how that mean, what that mean, right?
assuming there's no j.
There's no j, right? Okay, so I don't know if others see this, but pure imaginary by my mean is if you take the real of xj equal to 0. That means there's no real part, just the j times a real number.
So you said 3 was like.
AK is in x3 is.
So AK in 3 is purely imaginary.
Yeah, because this sign something is a real number, right?
Right.
So a real number times j is pure imaginary. There is no real part in this number. Yeah.
So x3 is pure.
X3 is not, but AKs in X3 is. AKs in X3 are all imaginary numbers. Just the imaginary numbers. Imaginary.
So why is X3 real then? Because the current part is 0 and 0 is 1.
X is real is like it satisfies this condition. So it's all imaginary, so the real parts are 0, so this one satisfied, and the imaginary part of that is sine, and we have already calculated here is a minus k is minus ak, and that's all imaginary, so it is satisfied this odd symmetric thing. I try to explain this another way.
So if it's 0 all the time, then that can be even or odd. If it's 0, then that's even and odd at the same time.
But if
Yeah.
if AK is 0, then x3 is 0. So there's no x there. Really?
Okay, let's see. The real part of AK is 0. So and the real part of AK, a minus k, is also 0. So they are equal. And the imaginary part of AK is sine k, and the imaginary part of a minus k is sine minus k pi 2, and that equal to minus imaginary part of AK. So this satisfies the Sankey condition.
Another way to actually think about it, if you look at that, that's equal to AK pi. It's only if that's an odd. So if you prove that the imaginary part is asymmetric, then that's an odd factor, and odd has an odd. So that's why.
Okay.